All right, thank you guys. Thank you so much, Miss Ashley. I really appreciate it. And thank you guys for being here. And I know you probably expected somebody to come in and talk to you for an hour, but I am horrible at doing that. Just a little bit about myself. Exactly. We're going to do some fun stuff together, I promise. I'm going to need 2 volunteers. Let me get you right here.
Wow.
Yeah, come on. And let me get you right there. Come on. Yeah. And what? Can you help me? You can help too. Can you help pass these out, 1 per person, to the people over here on this side?
Everyone on that one?
Everybody on this side. Okay. If you could help pass these out to the people over on this side. All right, thank you guys so much. I appreciate y'all being so helpful. I got great helpers here. All right, hey, let's give a hand for our helpers. You know what I'm saying? Y'all just volunteered. Y'all didn't even know what I was going to ask you to do. That's a good thing. All right, so as those are being passed out, and I can project a little bit because as I'm talking, I'm going to give you a little bit about myself. So my name is Benjamin Brooks. I taught in a traditional public school for 4 years after graduation, but my story goes back way farther than that. I was homeschooled from 5th grade all the way through 12th grade. I did get into college despite some of the myths. I got into college at the University of Alabama at Birmingham with quite a few different scholarships, I might add. So once again, possible, very, very possible. I graduated with my bachelor's degree in mathematics, and then I turned around and got my master's degree in education because I fell in love with teaching kids. And so I ended up teaching. Thank you so much. I ended up teaching for about 4 years or so in the Hoover City school system in Hoover, Alabama. And then after 4 years of teaching, I started teaching at my alma mater, the University of Alabama at Birmingham, teaching pre-calculus and calculus. And then now what I do is funny. I teach teachers, literally. So that's what I do. I help teachers. I help people learn about how to teach math. And one of the things that I'm doing with my company, shameless plug, my brewing tutoring company, is I help parents to learn how to teach math to their kids, homeschooling parents. So it's full circle for me. I started in homeschooling and I've come full circle all the way back. So I have a question for you tonight. So let's see. Let's say there are 20 people. There's way more than 20 people in this room. Okay. But let's say there were 20 people in the room because we're going to keep it easy. If every single person shook hands with everybody else, how many handshakes would that be? How many handshakes would that be? So it's 20 people. I'm going to give y'all a couple of minutes to think about it. There's 20 people. There's 20 people in the room. Okay. And if every single one of those 20 people shook hands with everybody else, how many handshakes is that?
40. 10. 200.
200. Why is it, I'm hearing 200, 400, 4,000. What do you think?
280.
380. That's very specific. All right. Well, let's see. Anybody else? 3.1. That works. Okay. All right. Well, stick around to the end to find out. All right. I know. All right. Take a look at the papers that you all were handed out. This is something that I like to do with a lot of the groups that I work with, is simple patterns. So in my description of this talk, one of the things that I said we were going to do is start with linear relationships and move on to more advanced, complicated things, potentially. But considering that it's a lot of kids in the audience, I want to keep everybody engaged, we're going to stick with the linear, which is totally fine. But I'll explain everything that I just said in just a second. So everybody sees what you got in your hand, which is great because I don't have a projector. All right? So everybody's got this thing. It says cow pens at the top. And here we've got the High Mountain Fencing Company is in the business of building cow pens. The company ships cow pens to all parts of the United States. To cut costs, they have found a way to build pens using fencing sections. So for example, a pen for 3 cows looks like this. You all see that at the top, right? The first one. A pen for 1 cow looks like so, and a pen for 2 cows looks like so. So your question is, how many sections of fence? Do not say the answer out loud. I really am a school teacher, so I know I have a little tricks and stuff. How many sections of fence would it take to hold 100 cows? I promise I'm going somewhere. But how many sections of fence would it take? If you have a pen, that's great. If you need a pen, I have like 3 or 4, and I'll try to help you out. But I want you to think about it. How many sections of fence would it take to hold 100 cows or 1,000 cows? So you all can talk amongst yourselves, but don't shout it out the answer to everybody. I want you to think, this is for everybody, all ages. So if anybody, I'm gonna walk around, I'm sorry to the camera person, but I'm gonna walk around and I can help you guys out but I'm gonna give you a minute to think about it. I'm gonna give you a minute to think about it.
Look for the pattern, right?
Do you all get? Yeah, for sure. Yeah, no problem. Yeah. If you think you got it and you want to talk to me, I'll come take a look and see what you got.
Here's how I do it.
Yeah.
You've got 3 there for 3 cows,
Sure.
1 there for 1 cow, and 2 there for there. So you'd
Sure.
have 100 there,
Right.
100 cows.
Right.
And then you'd have 101, 102, 103, and then another 100. So that's 203, 204, 205, 206.
That's correct.
Is that right?
Yeah.
Okay.
Yeah, you got it. So 1,000 would be pretty kind of simple from there. Yeah. Anybody else? Yeah. Anybody else? Oh, let's take a look what we got.
So 206.
Yeah, but how'd you do it?
Each cow has 2
Okay.
top and bottoms and a 3 and a 3. So 200 across and 3 and 3.
That works. That works. Anybody else? Well, I'm gonna come back over here, I promise. Yeah.
I got 44 because if you make it into a square, it would be 40, well, it would be 10, 10, 10, 10, and then the 4 corners.
So it's kind of like if you, basically you're taking this idea, but you're kind of like expanding it for the cows. That could work. What you guys get?
I got 206 because there's 3 for the 3 cows, 1 for the 1 cow, and 2 for the 2 cows. So if it's 100, then it would be 100, 100, and then 3 on each side. So 206.
So you're saying that the only thing that's changing is just the top part?
Yeah. And the bottom.
Interesting. I'm not gonna say if y'all are right or not. You might be right, you might be wrong. I'm not gonna tell you. All right, y'all get it over here. You got an idea? Yeah. Go ahead.
306.
You're close.
Okay.
You have the right idea. You're definitely right with the 6.
Okay.
All right. You said 306, right? Okay. All right. So for the first problem, I'm sorry, I was gonna come back here. Y'all, somebody has it? No. Okay. All right. So I know everybody is aching to know what the correct answer was, right? Well, I'm not gonna tell you. No, rather, I want you to tell me. So anybody that did it, I don't care if you got it right or got it wrong, or I didn't tell you. Can you explain it back to me? I'm gonna go here and then I'm gonna come. Go ahead.
17.
Yeah, go ahead.
looking at the 1 cow square, and each cow has a top and a bottom. So 2 times the number of cows plus 3 on one side and 3 on the other side. So I have 206 for 100 cows.
That works. That works. Let's see if, I'm not saying you're right, I'm not saying you're wrong. We'll see if we agree with you. What about you? What did you get?
I agree.
You agree? You did it. Did you do it the exact same way, or? Okay, yeah, go ahead.
So I just expanded it, so 10 times 4, 40, and then you add 4 for the extra ones on each side, so that's 44.
So in other words, instead of expanding just horizontally, you expand it horizontally and vertically. Okay, now if we take a look at the 3 examples that we've got in this particular problem, does it look like they're expanding vertically as well, or just horizontally? Just horizontally in this particular sample, right? But that's a way of thinking about it, right? I think you all can see exactly where we came from that. And this is one of the things I wanted to kind of talk about a little bit, because I'm sorry I'm moving a little bit off script, but I'm a teacher. It's just in me to talk about it. But one of the things that I often stress with teachers is, if your student gives you a wrong answer, don't just be like, no, that's wrong. Be like, explain your thinking. Why are you thinking that way? You see what I'm saying? Why did you come up with that answer? Because that answer is extremely plausible. Now, that's not the correct answer for this problem, but that answer makes sense. Y'all see what I'm saying? So when you're teaching your kids, especially in math or science for that matter, we know in science stuff happens, people get stuff wrong all the time, right? Didn't Alfred Nobel like blow up his brother or something? You know what I mean? Like it's a very important thing to understand that, like, we can talk about that. So that was very, very good. Other thing that I did was I had you all, rather than automatically telling you what the answer was, I let you mull it over a little bit, right? Because I could have just told you, hey, you know, you do 10 up here, 10 down here, and blah, 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 it's it. But what I did was I let you kind of think about it, you mull it over. And some people were might get a little bit frustrated, but that's okay. That's 100% okay. It's all parcel to it. Now, what does that have to do with number patterns in nature whatsoever? So this pattern that you all found is, we started with the 6 on either side, right? The 2 columns on both sides. All right, and then from that, you all are able to ascertain that as we add cows, we're adding 1 section above, 1 section below, right? And then we were able to keep doing that and doing that. All right, does anybody, for the adults in here, does anybody remember y equals mx plus b at all from high school? Does anybody remember y equals mx plus b at all? Yes? Yeah. So check this out. What you all just experienced is literally y equals mx plus b. I'm gonna explain. I'm gonna explain this for you that have never seen it before. I'm gonna explain what we're talking about. Though, if you look at your papers, those 6 on either side, right? Those 2 columns of 3 on either side, they're always there, right? So, and no matter how much you expand, we're always talking about that. That's constant, right? So that's what we were supposed to teach you, was the y-intercept. That's the constant. That's our starting point. It's where we start from. That's the thing that's always there. What the number that we were adding each time, because we were actually adding not one, we're not just adding 1 each time, we're actually adding how many each time? 2, right? Because we're adding 1 above and 1 below. That number that we're adding every time, that was your slope. That was your, in calculus we call it rate of change. Because that's how much is going up every single time. All right? And so if you think about it, what we've done is we've created and y'all can write it down if you want to. I'm sorry, I'm a teacher, it's just natural to me. But you can write down that the number of tiles that we had, what you can write is just y. So you can write little letter y if you want to. So the number of tiles that we had, which represented of y, equals 2 times x. X is going to represent the number of what? Cows. Exactly. X is going to represent the number of cows. Y represents how many tiles. But Y equals 2X is incomplete in this particular situation, correct? Because if you have Y equals 2X and your X is 1, you should only have 2 tiles. But what are we missing? What's the last part we need to add on the end?
6.
The 6. So in this particular situation, we got Y equals 2X plus 6 is representative of this particular pattern. Did everybody kind of see that? Y'all see how the two are combined or work together? Now, is that more or less impactful than just telling your kids Y equals 2X plus 6? Y'all see what I'm saying? And so one of the things we want to talk about if we're talking about number patterns in nature is we see this linear pattern or relationship all the time. For example, if, let's say, you get an advance from your job, which doesn't happen very often. It depends on what industry you're in. I mean, in the music industry, unfortunately, it does actually happen a lot. But let's say you get $100, right? Or whatever it is. And then from that, you make $15, or let's go with a bonus. Let's say you start with a bonus at your job of $100. And you make $10 an hour. Can't you all see how this is the exact same situation, the exact same relationship? You come up with the exact same thing in this particular instance from that. Anything in many of the things that we see in nature start with something. That's our B, that's our constant. And then it grows from that. Does that kind of make sense? And whenever we talk about something that's linear, we're talking about something that starts somewhere and then grows at a constant rate. Does that make sense? Now, that's not the only way things grow in nature. As a matter of fact, that's the most simplistic way things grow in nature. So, you know, not to get too technical, but if you're born, you start at age 0, at least while it's here, we do. Start at age 0 when you're born, and then every year we add years, right? So your age is a very linear relationship to how many years you've lived. Does that make sense, right? So that's linear, but there are other things that, well, it's not so linear. And so for that, I'm going to talk about one of my favorite mathematicians, which is Carl Friedrich Gauss. Gauss, and I promise I'm not going to talk too long, but Gauss was in kindergarten, or so the story goes. All right. And Gauss was in kindergarten, and the teacher at the board was writing these numbers to the board, and Gauss was just getting bored. He was getting disinterested. He was crumpling paper up like many people who are not homeschoolers do because they're just sitting in a classroom for 8 hours a day, and they can't go anywhere. You know, y'all wouldn't know anything about that, but anyway. Gauss was sitting there, and his teacher was like, I got to get this guy something to do. He's really smart with numbers. I'm going to say, Gauss, and you're going to be Gauss for a second, I'm sorry. But Gauss, I want you to add up all the numbers from 1 to 100. That's a pretty tall task for a little kindergartner, right? I mean, you would think so. I mean, because 3 plus 4 and then carry the 1 and 10 plus, but you know how long it took Gauss? I don't know, maybe 3 minutes. He came up to the front and he told his teacher's like, I got the answer. I'm pretty sure it's 5,050. And the teacher's stunned. The teacher doesn't know, how did you do this? Because Gauss found out something that we're going to talk about a little bit, which is a step up from linear relationships where you start with something and grow up, to something I want to talk about tonight you may or may not have heard of called triangular numbers. So I'm sorry, but write it down. Triangular numbers. And this is a very interesting relationship. So I wish I had some blocks, but it is what it is. I forgot I left them. But
Blocks? What kind of blocks?
just like regular, but I need a lot of them.
A hell of a lot.
Uh-oh. Watch out now. Watch out now. All right. So what I'm going to be talking about is how the linear relationship align. You got this idea of we start with something and then it grows and grows and grows and grows at a particular rate. But imagine, if you will, while they're trying to get that for me. what if you took, and I know pretty much everybody's played with building blocks or Legos at this point, right? Everybody has, right? So imagine if you took one block, right? And then what we did is you put 2 blocks under that, okay? So if you would, turn your paper over and let's see if we can kind of draw or think this out, because I promise you I'm gonna make a good point with this. So I want you to draw like one just square block at the top, and then maybe 2 square blocks right underneath it. It is what it is. So we got 1 square block at the top, 2 square blocks underneath it. How many blocks are we looking at right now? How many do you have in total? You got 1 square block and then 2 square blocks underneath it. How many we have in total? 3, right. Now, let's go a little bit further. So we took that 1 block at the top, we got 2 square blocks under it. Now we're gonna do 3 blocks under that. Y'all see where I'm going with this? Right? So we got 1 block here, 2 blocks here, and 1, 2, 3 blocks under that. So we got 1 block, 2 blocks, 3 blocks under that. How many blocks do you have?
6.
6. All right. So we got 1 block. See, y'all have great imaginations. I love this. All right, we got 1 block, 2 blocks here, 1, 2, 3 blocks under that, 1, 2, 3, 4 blocks under that.
10.
Oh, that's perfect. Perfect. I don't think I heard it. What was the answer? Yes, absolutely. 10 blocks. So, and this is actually a great thing to do when you have manipulatives. But we've got, I don't know if can y'all see that from back there? Okay. So we got 1, 2, 3. Let me go. I'm gonna go to 5. All right. So that's at 5. And when you get to 5, 1 row at the bottom, how many do you have? 5. So we got 1 at the top, then 2, then 3, then 4, then 5. How many total?
15.
That is correct. All right. Now, part of the reason why these are called triangular numbers is because geometrically you all can see them as triangular, right? It's literally a big old triangle. As a matter of fact, I can make this triangle look I'm gonna try to keep this from falling over. But I actually can make this triangle turn into a right triangle, like that. And now what does it look like?
A hair.
A staircase. Exactly, exactly. It kind of looks like a staircase, some steps and whatnot. All right. Now, here's what Gauss did. What we've been doing tonight, I gotta check and see how much time I got. Oh man, I got 10 minutes. All right. So what we've been doing tonight has been called induction, or inductive reasoning. In other words, you started with a small sample size, you figured out how something worked, and then you took that and you thought about what would happen if we put this on a bigger scale. With the first problem we did, the cow pens problem, you had only 3 examples, right? You only have 3 examples. You figured out what happened in those 3 examples, and you put it on a bigger scale. So here's what Gauss did, because it's kind of amazing. What Gauss did is he said, hey, look, I've got these numbers, I've got these things, but what if, I'm gonna try to use just white blocks I promise I'll clean all this up, but I'm gonna try to use white blocks to kind of illustrate this point here. What if, instead of thinking of these blocks as or thinking of numbers as just merely just numbers in terms of just numbers, what if I think geometrically about doing something like this? These white ones that I'm going to put down kind of represent this space.
It's a square. A square.
Yeah, it's a square. Yeah, absolutely. It's a square right now. I think I'm about to run out of whites, but y'all roll with me. I promise I'm going somewhere. So it was a square first, but what does this actually kind of look like? A rectangle. And not only is this rectangle just a rectangle, regular rectangle, but what are the dimensions of this rectangle? Well, it's 5 by how much? 6. And which row were we on at the time? We were on row 5. So here's what he did. He said, if I take the row that I'm on, the 5, and then I multiply it by one more than that row, the 6th row, right? I can create the area of a what shape is this? Rectangle, because rectangles are easy to do. This is base times height, correct? So what he said was, I take the row, multiply it by this height, and I realize that this white area is the exact same as mine. So you know what I can do? I can cut it in half. So that's what Gauss did. He said he took 100, he multiplied it by 101, which is going to be 10,100, and then he cut it in half, 5,050. And that's how he did it. So, so what he did was he said, hey, if I add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, I'm going to take that 7, multiply by 8, get 56, and cut it in half. It's going to be 28. You kind of see where the pattern is going here. So I promised you that I was going to give you the answer to the first question I gave you, right? Which was if there were 20 people, in here, then how many handshakes will there be? Well, I want you to think about it. Let's make it on a smaller scale. Let's say there were 4 people in here. How many handshakes will there be?
4 handshakes.
Well, let's think about it. So you got this one person who's going to shake hands with this guy, right? And then this one person is going to shake hands with this guy right here. I got to be careful with my fingers. And we got one person who's going to shake hands with this guy right here, right? That's 3 handshakes. And then this guy is going to shake hands with this guy right here. That's 1. So this guy's going to shake hands with this guy right here. And then this guy's going to shake hands with this guy. That's 6 handshakes. As a matter of fact, if you think about it, for 4 people, we're literally looking at the 3rd rung. We're looking at this right here. So, which is 6. So what he did, so the answer to this question is, I'm still not going to tell you. I'm going to let you go home and think about it. And I'm done. I'm done. Did I hit it right at 7:30?
No.
Oh, dang. Did I have to tell y'all the answer? Oh, Lord. Let's talk about music.
You would like to leave, but
Stereotype right now.
Actually, let me do this right here. Y'all like, what in the world is wrong with this man? This has nothing to do with anything we talked about. All right. So, when we came to the 20 people in the room, all you had to do was take 20, because somebody said the answer correct earlier. I can't remember who it was, but you were correct. You took the 20, multiplied by 19, it gives you 380. But then you actually, the one part you had to do was cut it in half. That was the last part to do. You had to cut it in half. And then that'll get you to what? 190? So 190 was actually the answer, but you were real close. You just forgot to cut it in half. Which is why when I heard it, I was like, ugh. All right. So one of the things, the last thing that I did want to talk about, this is why I brought this out. I didn't know if I was going to get to it or not, but anyway, is that we see patterns everywhere, right? So this goes to our broader theme of we see patterns obviously in blocks in nature in terms of things growing. Like, for example, if you think about a linear pattern of geese flying, we start with that 1 in the middle, and then they grow 2 by 2 by 2 by 2. If you all ever see geese flying like that, that's another pattern that we see. And the reason why these patterns are interesting is because patterns are nice. Because it gives us a sense of order. It gives us a sense of direction, like we know where it's going. I bet I can stop playing right now. You can probably figure out in your head where I'm going next. Where to go next? Where? Yeah, some of y'all, it's like, especially the musical people, like, play that last note. Resolve that thing. So, unfortunately, patterns can be used, overused, as we know, right? Because this particular pattern right here, we hear in a lot of songs, like, never mind, I'll find someone like you. I wish nothing but the best for you too. Or just a small town girl living in a lonely world. So we see patterns over and over again. We see patterns in music. We see patterns in nature. We see patterns in blocks that I now have to clean up. We see patterns in cow pens. We see patterns in another thing that if you want to come and talk to me afterwards, I have another. If you really like this activity, I've got a ton of them. I will share with you for absolute free. No charge or whatever. So if you're interested in something like that, or if you want to talk to me afterwards, I'll have a few minutes. And I don't mind giving you my information and we can kind of work on these, because the truth of the matter, guys, is yes, patterns are great and we see patterns in nature, but I would say the overall theme really of my talk tonight would be math doesn't have to be boring. And it doesn't have to be just memorization of facts or things or formulas. These formulas actually mean something. And then once you capture that greater meaning and can pull those out of your students, it'll create much more meaningful connection. And I mean, I'm here to help with that, because to me, math, I learned math this way, which is why I don't think math is hard in the traditional sense. But the truth of the matter is, you don't have to do what most people do. You can do whatever you want. And more importantly, you can find greater and deeper meaning for math education for your family. And so with that, I really am done this time. Thank you all for listening.